Okay, let's dive in. Imagine this. You're playing poker, right? But it's like totally decentralized.
Hmm.
Every single card you get, every bet, every bluff, boom, everyone sees it instantly.
Yeah, talk about pressure. No secrets at all.
Exactly. And that's kind of the problem we're looking at today with public blockchains. They're amazingly transparent, which is fantastic for trust, but, well, it's a real issue if you need any kind of privacy.
It really is the core tension, isn't it?
Yeah.
You've got this network built for everyone to see everything, but how do you handle private interactions on it? How can you have, secret data sitting on a public chain, but still control who sees it and when?
Right. And our source material today points towards a really interesting solution, something called trusted execution environments, or TEEs. And it focuses specifically on how one project, the Byte protocol, uses Intel SGX technology, a type of T on the SKALE network, to try and solve this.
Yeah, that's the plan for this deep dive. We're going to unpack how Byte, according to the source, uses Intel SGX to basically add that privacy layer onto the blockchain. How does it actually work?
So let's maybe zoom out for a second first. Before Byte, before SGX even, what is a trusted execution environment? The source uses a pretty neat analogy.
It does, yeah. Think about your computer, okay? Imagine it's like a big open plan office.
Okay.
Most stuff happens out in the open. Your web browser, your documents, system processes, they're all kind of working at desks where anyone could theoretically look over their shoulder.
Right, visible.
But what if you need to do something really sensitive? Like, I don't know, the source says, counting a big pile of cash, writing a very personal letter.
Or maybe the more extreme example they gave, handling nuclear launch codes.
Exactly. You definitely wouldn't do that out in the open office.
No way.
You'd need a secure, locked room, a private space inside that office where you can do that sensitive work and be absolutely sure nobody outside can see in or interfere. That locked room built right into the computer's processor. That's basically what a T is, a secure area just for sensitive operations.
And the source says this secure room has, like, 4 crucial features, almost magical powers.
Yeah, that's a good way to put it. First up is isolation.
Okay.
Whatever code or data is inside that T, it's completely sealed off. The main operating system, the hypervisor, even if there's malware on the computer, none of it can get inside to see or mess with what's happening. It's like its own little bubble.
So totally separate from the rest of the system's operations.
Precisely. Number 2 is integrity. This means the T guarantees that the code running inside it is the correct intended code. You know it hasn't been secretly swapped out or tampered with.
So you can trust the process is running as designed.
Exactly. Third, and this is really key for privacy, is confidentiality. Any data processed inside the T stays secret. And critically, this means even the person who owns or operates the physical machine cannot see the data while it's being processed inside the T.
Whoa, okay. So data goes in, secret calculations happen, and even the owner of the box can't peek inside. That's pretty significant. What's the fourth one?
The fourth is attestation. This is how the T can prove to someone else, like over the network, that it is a genuine T and that it's running a specific verified piece of code that hasn't been altered.
So it can sort of vouch for itself, like showing credentials.
Exactly. It's like the secure room can issue a digitally signed certificate saying, yep, I'm a real secure T, and I'm currently executing the official Count the Votes program, version 1.2.
That attestation piece feels really important for building trust, especially in a decentralized setting. You don't trust the machine owner, maybe, but you can trust the TE on that machine because it can prove itself.
It's absolutely crucial. It allows external parties to verify both the hardware security and the software integrity. And, while we're focusing on Intel SGX because of the source, it's worth noting this isn't just Intel. The source mentions others like AMD SEV, ARM Trust Zone, which you find in phones, and even open source projects like RISC-V Keystone. They're all aiming for the same goal, creating a secure space for code on hardware you might not fully trust.
Okay, got it. So that's the TE, the secure private room in the chip with these 4 powers: isolation, integrity, confidentiality, and attestation. Now, let's connect it back. Blockchains. We said they're transparent. Why is this T concept so relevant for them?
Well, like the source puts it, blockchains are fundamentally glass boxes. Their whole value proposition is built on everyone being able to see the ledger and verify it.
Yeah.
That's where the trust comes from. You don't need a middleman because it's all public.
Right. The trustless idea.
But that transparency is exactly the problem for a lot of real-world applications. You need confidentiality for so many things.
Like the examples mentioned in the source, right? Sending a private message that only the recipient can read.
Exactly. Or running a sealed bid auction where you don't want bids revealed until the auction closes.
Secure voting, maybe?
Perfect example.
Yeah.
Or even storing something like a digital will that should only unlock under specific conditions later on.
Yeah, you can't just put that raw data on a public chain.
Nope. And even if you encrypt it and put the encrypted data on chain, you still face the challenge. How do you decrypt and process it securely later? Who do you trust to do that decryption without leaking the information?
Ah.
Keys potentially bridge that gap. They allow for the outcome of a computation to be publicly verifiable on the blockchain, but the process itself, using the sensitive private data, happens securely and privately inside the T.
So public proof, private process.
You got it. And this brings us to Intel SGX, which the source positions as the enabler here, like their magical black box idea.
Tell me about the black box.
So the source asks you to picture this, a box. You put encrypted data into it. Inside the box, hidden from view, it gets decrypted. Then some code runs, maybe it figures out the highest bidder in that sealed auction. And then the box just spits out the result, maybe the winner's address and the winning amount. But crucially, the encrypted bids that went in and the process of comparing them inside, totally hidden, never exposed.
Takes secrets in, does secret work, gives a public result out. I like it.
And Intel SGX is basically a real-world technology that does this, a hardware feature in some Intel CPUs that lets software create these secure zones called enclaves.
Enclaves, okay.
The source uses the analogy of a tiny Fort Knox built right into the CPU chip. It's this protected area of memory. Data can go into the enclave, trusted code runs inside it confidentially, calculations happen, and then results come out. Anything outside the enclave, the OS, other applications, the machine owner can't see or interfere with what's going on inside.
Okay, so SGX provides the Fort Knox enclave. Now let's get specific. How does the Byte protocol use this technology on the SKALE network to actually achieve privacy for users?
Right. So Byte is implementing this on SKALE. And the source mentions SKALE provides these, high throughput, zero gas feed chains, which helps with the kind of computation involved here.
Makes sense.
Byte's approach, as described, involves users encrypting their data off-chain first. Then instead of relying on one server, it uses a decentralized committee of nodes on the SKALE network, where each node in the committee is running Intel SGX. These SGX nodes work together to handle the decryption.
A committee of SGX nodes, decentralized trust again. That sounds important.
Absolutely key. It avoids central points of failure or control. So let's walk through the steps for what the source calls Phase 1, threshold encrypted transactions.
Okay, step by step.
Step 1, user, you want to send something private, a vote, a message, a bid. You encrypt that data before it goes anywhere using a shared public key.
A shared key, like a padlock that the whole group uses, but the actual key to unlock it is split up somehow.
That's a really good way to think about it, yeah. It's a public key, but the corresponding private key isn't held by any single person or node. It's fragmented.
Got it. So encrypt with the shared key. What's next?
Step 2, you take that encrypted blob of data and you submit it as a transaction to the SKALE blockchain. It gets recorded on the public ledger. Everyone can see this encrypted blob exists, but nobody can read it. It's just scrambled data. The chain is holding the lockbox.
Okay, locked box is on the public chain. Now what?
Step 3. When the next block is processed, this committee of special SGX-enabled SKALE nodes sees the encrypted data. Each node in the committee pulls that data into its own secure SGX enclave.
Into their own little Fort Knox.
Exactly. And this is critical, the source emphasizes. The people running those nodes, the node operators, they cannot see the actual plaintext data. Yeah.
Uh,
It only gets decrypted inside the secure enclave, which they can't access.
So the node operator is blind to the sensitive content. Good.
Very good. Now, step 4, the threshold part. This is super important. No single SGX node in that committee can decrypt the data by itself.
Ah, okay.
Remember how we said the private key was fragmented? They use a technique called Shamir secret sharing. Each SGX node in the committee holds only a piece of the private key. They have to work together, combining their fragments within their secure enclaves to reconstruct the full private key and decrypt the data.
So you need a certain minimum number, a threshold, of these SGX nodes to cooperate honestly inside their enclaves to actually unlock the data.
Precisely. That's the threshold cryptography magic. It ensures decentralization and security. Step 5. Once that threshold is met and the committee of enclaves successfully decrypts the data together, the now plaintext data is immediately passed to a specific function within a smart contract running on SKALE. The source suggests a function may be named on decrypt. This is where the application logic happens. The smart contract takes the decrypted vote and counts it, or takes the decrypted bid and determines the winner, or processes the private message content.
So the smart contract gets the secret info, but only after the secure threshold decryption by the SGX committee. And the final step.
Step 6. The result of that smart contract execution, like Alice wins the auction, or the vote passes, or maybe just a confirmation the message was processed, that result is written back onto the SKALE blockchain.
Okay.
So the outcome is public and verifiable for everyone, just like normal blockchain stuff.
Yeah.
But the original sensitive data, the bids, the votes, the message contents, it remains hidden. It was only ever plain text inside those secure enclaves, never on the public chain, never visible to the node operators.
Wow, okay. That's quite a process. Off-chain encryption, on-chain storage of the ciphertext, then this coordinated secure decryption inside multiple Ts using threshold keys, feeding the result to an on-chain contract, and finally publishing just the outcome.
Yeah, it's pretty intricate.
But it does raise a question which the source anticipates. Why bother with all the SGX complexity? Why not just say, encrypt your data and send it to 5 regular servers run by different people and ask them to decrypt it using threshold techniques? Why not just trust the nodes?
That's a really crucial question to address, because trying to do this without the hardware security of Ts like SGX introduces some major risks, which the source highlights.
Like what?
Well, imagine you send your encrypted bid to 5 standard servers, not SGX nodes. What could go wrong? First, one or more of those server operators could just leak your secrets. As soon as they decrypt your bid, they could copy it and share it.
Right. Defeating the entire purpose of keeping it private.
Completely. Second risk. They did lie about the result. Maybe they decrypt all the bids, see that you won, but then collude to report that someone else won, writing the wrong outcome to the blockchain.
So they tamper with the output, bypassing the blockchain's integrity.
Exactly. And third, without a T protecting the execution environment, a hacker could compromise one of those servers. They could potentially install malware that steals the decrypted data, or worse, alters the code that's supposed to be running, making it calculate the wrong winner or leak information subtly.
Okay, those are serious risks. Leaking, lying, tampering. And SGX, with its TE powers, is meant to prevent these.
That's the whole point. Let's go back to those 4 powers. Confidentiality means SGX guarantees decryption happens only inside the secure enclave. Integrity and attestation mean you can verify that the correct, untampered code is running inside that enclave. And isolation means nothing outside. Not even the node operator or malware can interfere with or observe the process inside.
So it locks down the computation itself.
Right. And when you combine this SGX security with the threshold cryptography across multiple nodes in the byte protocol.
Then you're not even trusting a single SGX chip or a single node operator.
Exactly. You move from needing to trust individuals or individual machines to relying on threshold trust across the decentralized committee. Even if, say, 1 or 2 SGX nodes were somehow faulty or malicious, as long as the required threshold of honest nodes correctly perform their part within their secure enclaves, your data remains confidential and the computation result is trustworthy.
Okay, that makes a lot of sense. The T protects the computation on each node, and the threshold mechanism protects against failures or malice among the nodes.
Precisely.
All right, let's try and summarize this, maybe using the source's own TLDR points.
Sure. So the big picture is, 1, blockchains are transparent by design, which is a problem for privacy.
Sure.
2, technologies like Intel SGX provide a way to create a secure black box and enclave for computation, even on potentially untrusted hardware, and this can be done across many nodes.
Right, the tiny Fort Knox.
3, the byte protocol uses these SGX enclaves on SKALE, combined with threshold techniques, to process private data like encrypted transactions or votes without exposing the raw data itself.
Keeping the secret secret.
And 4, that threshold encryption part is key, ensuring that no single node can cheat the system or reveal the private information on its own. You need the group consensus.
Okay. And the source suggests this isn't just, a neat technical trick. It implies this kind of capability could really change what blockchains are used for.
Yeah, it positions it as a step towards blockchains evolving from being just public ledgers, just recording transactions, to becoming actual secure compute platforms. Platforms that can handle sensitive information reliably.
Which really opens up the possibilities, doesn't it? When you think about decentralized applications, what kinds of things become possible for you as a user or maybe even a developer when you can finally trust a public blockchain system to handle private data securely?
Oh, loads of things. Think about decentralized identity systems where your personal info stays private. Or confidential DeFi may be strategies that rely on secret information. private voting systems that are actually trustworthy, secure ways to manage sensitive records like health data or legal agreements, where access rules are enforced by smart contracts acting on TE decrypted data.
Yeah, the potential application space seems huge once you solve that privacy piece in a verifiable way.
It really does. It unlocks a whole new category of applications that need both blockchain's transparency and coordination benefits and strong data confidentiality.
It definitely leaves you with something to think about. If we can use these secure enclaves like SGX plus these clever crypto techniques like threshold decryption to process truly private data on public chains, what's the next step? What other kinds of complex, sensitive computations things currently stuck in centralized databases or private servers might we eventually see being managed and coordinated by blockchains?
That is the really exciting forward-looking question, isn't it? How much sensitive real-world logic can we shift onto these decentralized, trust-minimized rails while keeping things appropriately confidential?
It's a fascinating direction. And just as a final note for listeners interested in the wider context, the source material also mentions some other things happening around SKALE, like their indie game accelerator program and ongoing engineering updates. So seems like a lot is happening in that ecosystem as they build out these kinds of advanced features.
Yeah, definitely an active space to watch.